Hello, welcome back to error analysis. So, as you'll recall, last time we started talking about measurement error, and we said broadly we imagine a single measurement to be made up of its actual value plus some error, right? And so remember that the actual value is the thing we really want, but in practice we can't have it. We can't actually have it. There is no infinitely accurate measurement device in existence, and there is no infinitely skilled operator in existence. And so every measurement has some error, right? And in this context, the actual value is unobtainium. It's the stuff you can't have. It doesn't. It only exists in theory. But we talk about it and we write it on the page because it's the thing we want to approximate as well as we can. So we've started developing some language to talk about that. So we developed the expected value, and we figured out that this was true last time. So if this is confusing, go back and watch error analysis 1. So that the idea of the expected value for any individual measurement is the actual value plus the expected value for error n. We then talked about there being two different types of error. We split this into random error, and we talked about systematic error. And that's where we're going to try to start to pick up the conversation today. So, for example, now in our class, the way we are going to draw this distinction, there are actually lots of different ways you can classify error, and there are lots of different thinkings out there as to how error should be and can be classified. For this class, the way I'm going to talk about it, we will talk about systematic errors as cases where this is not true. And random error we will talk about as cases where this is true. This is a somewhat sloppy, there's more to it than that. And this, you could there are types of random error that you could classify where that's not quite the case. But for us, for our conversation, and what we need to get across is we can conveniently and effectively, it's a useful tool to organize sources of error as error where on average the error will be 0, and error where no, you've got error every time, and it gives you a even your expected error if you performed 1,000 measurements would not be 0. So this, for example, was in the parallax error in last time. So if my height is different, so if my height causes error in how I read a ruler, for example, so there we go. That's how we're going to work at it. So here's the cool thing about that: if it's random, if the error is random, then that would mean the expected value for x is equal to the actual value. That would be truly exciting. So that gives us a mission. We want the expected value of error to be as small as possible. So systematic error. Now, this is maybe helping me build my case for why this is the hard case. This is the hard one. Okay. So yeah, and you can visualize it this way with random error. So I'm going to make a plot here of samples of error. So if I had 1,000 error measurements and I plotted them versus sample, right? You might get a cloud of points, and the idea is that, but they're all centered around 0, right? So this would be a case where the expected value of error is 0. Whereas with systematic error, you might get some well-organized right? And here, no. This is not random, right? This is clearly a systematic wandering, right? There's something deterministic, predictable going on here. This is something you might get, for example, as a sensor ages or warms up, or yeah. So this might happen. For example, if you have a strain gauge based sensor, as it heats up, its properties can change. You might see this kind of a wandering behavior as the sensor warms up. You might also see this kind of wandering behavior as an operator gets fatigued and starts taking less and less time and being less and less careful in their measurements. So this is the kind of thing that you can actually see in data. And isn't it amazing when you look at the two, how different they are in character? This is one of many reasons that we choose to categorize them separately. Okay. So here, clearly, we're going to want to start looking at statistics, right? So here we're going to want to start to try to characterize error. So we could have two very different sets of measurements in the random category. In this random category, we could have two very different sets of measurements. We could have a set of measurements that look like this. Right? And a set of measurements that look like this. Now, these two both have the same expected value, but my goodness, they have horrifically different magnitudes of scatter, right? And so if you take the expected value for both, they're 0, of course, right? And the answer for why that's true is there are as many negative values as there are positive values, and they're roughly equal in magnitude, so they all cancel each other out when you sum them up in the expected value, right? But that would not be true. That would not be true if I repeated this for the square of error. If I plotted error squared, all of these would become positive. You cannot have, because these are all real valued measurements, you cannot have a negative value. And I'll use circles to represent another, a data set with more scatter. Maybe you got a couple of good points in here. Oop, circles. So you could imagine two different data sets, x's being very little scatter, and then circles being lots and lots of scatter, or maybe 2 or 3 times as much scatter. So here everything is above the x-axis. So if I sum that up, that would become a pretty good measurement for the amount of scatter I have. And so we invent the idea of the expected value of error, of the square of error, as a measure of the amount of uncertainty in the system. This is the first idea we have. This is the first attempt we have to measure magnitudes of uncertainty. But this actually is this is pretty intuitive, right? If you just look at this is a really simple operation you could do on Excel data, or you could save yourself the pain and discomfort and learn a real language. This is pretty intuitive, right? So yeah, you sum up all of this, and it would look like this. It's the sum of now in statistics texts, what you're going to see, this n here is not. I am going to be very careless about this definition. In many statistics texts, you'll see an n-1 here and not n. Now, I am going to be talking about the case where n is very large, and so I'm going to get to be sloppy about it. We're not really going to have to think a whole lot about that. So just if you're comparing this with what you see in other courses, don't panic. It is actually the same. I'm just being sloppy about n's or n-1s. This gets what I really want is the idea that we're going to be looking at the amount at the magnitude of the square in error rather than just the magnitude of error, right? So these should develop two different ideas. All right, does that make sense? Good. I don't know why I'm asking a camera a question. Don't judge me. It's a hard habit to break. Okay. So, if that's the case, but we don't know what error is, and we don't know what any of this stuff is. So if random, dot, dot, dot. So if my data set is random, or if my error is random, rather, we already said that the expected value of x is equal to xa plus e, right? Expected value e. Okay, that's neat. And we said that this was going to go to 0. And so the expected value of x should, if everything is, if n is really a huge number, we just take a huge number, ridiculously huge number of measurements, this should be pretty much true. We'll deal with how that's not perfectly true later. All right, so we'll actually quantify how big should n be for this to happen. Okay, so that should be about true. Well, then what about error squared? Well, error, if I just rewrite things, error is my measurement minus the actual, right? Keeping in mind, I don't know the actual. I just, we think we know it. We want to approximate it. So this is the thing I actually measure. This is the thing I want. Okay, so if I say what is the expected value of error squared, whoa, this is going to get weird. Well, let's start substituting. So the idea, again, the subscript k means we're the kth measurement, so we're going to do this over a whole lot of measurements. Oh boy. Well, so in other words, one way to write this is weird. Maybe this will look a little more comfortable. All I've done is dropped in the expected value for x in there. If you haven't noticed, where we're headed is I'm developing the idea of standard deviation or variance. This is the idea of variance in statistics, right? So I'm trying to develop this from a pretty intuitive basis, right? And this is really where it all comes from. Okay, so this introduces some interesting ideas. We can actually go a little further and play with the algebra a little bit. So if I just rearrange this a little bit, we have some a convenient tool. So let's see, xk squared minus, oh how fun, 2 x sub k xa plus x sub a squared all divided by n. Interesting. So let's distribute that summation and see what we get. All right, so I can write these in individual terms. So the summation of a sum is the same thing as the sum of summations, which is a really massively confusing way to put into words what I'm about to write. So, in other words, that's just the same thing as expected value of x squared, that's this, minus twice the expected value of xk times xa plus, and then this is just the expected value of x sub a squared, right? Now, remember that xa is just a constant, right? So remember that xa is it doesn't change. It's this make-believe theoretical thing that we believe we know, right? We think we know. So it is just a constant. So in other words, this is precisely equal to xa squared. Right? We don't have to do any math there. So what is this? This is a random variable. Oh, I don't need the subscript inside of there. Oops, sorry. This is a random variable, or a variable that changes randomly, times a variable that is deterministic, that's a constant, right? How do we deal with that? Well, this is just the sum of xk, xa over n, which is, since xa is a constant, is exactly equal to this. I can factor it out. It's there in every term, so I can just factor it out. No problem. Absolutely. You can always, in fact, I could do the same thing with the 2 if I wanted. I can put the 2 inside, take it out, inside, out, doesn't matter. A non-random variable can move nicely inside or outside of brackets. That's what we just learned. Neat. So in other words, or excuse me, sorry, we already said that's just x sub a squared. All right, so not too bad. That's all equal to the expected value of error squared. So we've done a lot of moving around. Now, let's bring it home. So the expected value of error squared. Now remember, this is a measure of how much error we have in our system. So if I rewrite what I had, let me just rewrite what I had at the bottom there so we can all see it clearly. This is what I had at the bottom. And this looks pretty messy, right? So if error is purely random, we're going to say that this is true, that the actual measurement is in fact equal to the expected value of x. This is, as I've mentioned, a bit of a leap. That's not strictly true. But in the cases where that is true, this is going to work, right? So if we manage to reject all systematic error, which we can't, then this would be true. Okay, so if this were true, then so I'm emphasizing everything we're going to do. Everything is approximation because the world is messy and imperfect. All right, so in other words, I can write this purely in terms, what I'm trying to do is get rid of xa because I don't know xa, right? xa is the thing I don't know. I'm trying to get it strictly in terms of things I can measure. All right, so here we go. Minus, oh, look here, minus 2. If I substitute this in, I've got the expected value for x squared plus, oh, expected value for x squared. Weird, it is in fact Neat. So this is just another way of calculating what you may already know as standard deviation. Kind of a messy idea, but it actually works pretty nicely. So this is probably what you know as standard deviation. You may know this. So this would be the stat way of doing it. Or excuse me, this is variance, not standard deviation. So variance, the idea of variance, this is variance from statistics. So the idea of variance is the sum of the squares. How much does a measurement deviate from its average, is the idea. I have completely from scratch redeveloped that idea, just thinking about if I took 1,000 pressure measurements or 1,000 height measurements. Well, how could we quantify how well we're doing, right? And so that, I hope, will be motivated by what we've done here. And there are a couple different ways we can do it. We can either do it the classical, so this is using expected value notation. So you embed the expected value of x inside and you take the difference from that. Now let's talk a little bit about how that's actually calculated in practice. So if I had now a whole bunch of measurements, apparently we were having a really bad day right there. So yeah, if you have a whole bunch of measurements and you wanted to and you wanted to try to quantify the error, well, this dotted line here is what you would get if you averaged all of those. So there we would call that the measurement's expected value. So what that is saying, if I take another measurement, the next measurement, what do I expect it to be? I expect it to be at the middle of the data. It won't be. It won't be. There is precisely zero probability that it will be exactly that. We'll develop that idea in the future, but I'll cheat a little bit and warn you. There is no probability the next measurement will be exactly on that line. It will be within some window around that line. How do we establish that window? We do that by also measuring how much each of these measurements deviated from that line, right? So this right here we called the error. So each of these is an error. And so we summed up all of the squares of the error. What is the average square of error? Because we know that if I just average all of these errors, on average they'll be 0. But the squares, the average of the squares will not be 0. That will tell us, on average, how far am I from this line. And so we get, if the data were mashed up and were very tight around the line, we'd get a very small value for this. But if they were wide and spread out, we'd get a very big value for this, and we would know that our measurement was poor and that we didn't have good repeatability. We had a lot of randomness. And so I want to emphasize there are two ways. There are two ways to measure that. Now notice that x, though, right, is this distance right here, right? This is x, and this is x. Okay, so I can calculate, in summary, I can calculate error two different ways. I can either calculate the sum, I can take the average of the squares, or I can do this. And we'll do an example. Oh yeah, and I'm sorry, right, what do we and we call this the variance of x. This is the variance of x. The sigma sub x, I'm not going to talk about that a whole lot just yet, but I'm linking it because you'll probably recognize this from statistics, right? So I just want to show you that these ideas are linked if that idea already exists in your head. Okay, no problem. So let's go on. So let's, I don't know, this is where I would normally solicit the class for a bunch of random numbers. But no, let's go ahead and take a series of measurements. So forgive me if this is repeating something you know, but if, let's go back to the pressure example. If I were taking a whole bunch of pressures, I might get 53.1, 52.6, 54, or that's 54.1, forgive me. This is where I would, on the whiteboard, or on the chalkboard, erase it. So 53.5. And you can imagine, this feels about like what you might actually get out of pressure gauges, a series of pressure gauges. Notice I am not attributing the error to any source. I am making no assumptions about where this error came from. I'm just taking a measurement a bunch of times and we're going to see what happens. And one more, let's say 53.4, right? So I've only got 5 measurements. That's actually pretty poor in terms of a sample quantity, but it'll get the point across for our purposes. I'm going to make a little table here. So here's x. All right, and now we can actually write down here what is the expected value of this column. Right, so the expected value of x, well, I need my handy-dandy calculator. I am not going to try to do this in my head. That seems error-prone. All right, when I sum all these up, I get 266.7. So I need to divide by 5, and I get 53.34. And these might be in PSI, let's say. So these have units. PSI. Okay. So there's our expected value. So this row is expected values. All right, so if we wanted to measure the variance, so how much do these data vary? We've got a definition for variance right here. We see there are 2 equations. We could use this, or we can use this. Let's use this one first. This one looks easier. So in order to do this, I need to calculate the expected value of x squared. And here, I need to calculate the expected value of x, and I need to square it. Well, I already have the expected value of x. I just need to square it. So this part's already done. Now I just need to do this. So if I just add a column, and this one's going to be in PSI squared, or the units here, right? All right, so here we're going to have 2819.1, or 61, excuse me. I am going to carry a lot of sig figs, just because little rounding errors can accumulate here in strange ways. 2766.76. You can see this is the kind of thing where Excel would really pay off. But I'm going to do this exactly like I would normally do it on the chalkboard. My goodness, did I just say out loud that Excel would pay off? 2926.81. I understand how you make a software program that is entirely built around looking at huge gobs of data, but the statistics analysis toolkit is a separate toolkit. What do you do then? 2862.25. I've never been to a conference, not one, where anyone's ever presented a plot from Excel that the entire audience didn't immediately know that's a plot from Excel, because it looks awful. 28, 51.56. All right, so now I've got my column populated. I'm done complaining about Excel because now I actually need to actually do some work. All right, 2819.61. Oops, keystroke error. 0.61 plus 2766.76 plus 2926.81. Okay, and again, I get, when I sum all these up, I get 14,227. I need to divide that by 5, and I get 2840. 5 point, I'll go ahead and write out all the sig figs I've got. 398. We'll get silly. All right, so I've got that. Good. So this is the expected value of x, and this is the expected value of the square of x. So the variance of x, which we said was equal to the expected value of error squared, is the expected value of x squared minus the expected value of x squared, or the expected value of x squared is this. Now this is going to be 53.34 squared. All right, so here we go. 53.34 squared. 2845. So this is 2845 about 0.16. So 2845.398 minus that. I get 0.2424. Now, what are the units on that? The expected value of x squared is in psi squared. The expected value of x is in psi squared, though. So this is in psi squared. That's why I'm writing the variance as this square here, to imply that this is going to be on x. So this is not a deeply intuitive quantity to us. It is a measure of how much variability we have in the measurement, how much the measurement changes when we repeat it. But it is not deeply intuitive. To put this in calibrated terms, that is in units of engineering interest, we can take the square root of that and find the standard deviation, which is, if this looks, oh, whoops. Oops. This is what I meant to write. This is starting to look goofy. Yeah, it's goofy. That's one of the reasons we invent variables for these things, which is just the square root of 0.2424 psi squared. Or about half a psi. So it's 0.4923. That's probably more sig figs than I need. In fact, I know it's more sig figs than I need. So what you see is, what that means is the order of magnitude, how much variation do we have? About half a psi of error. Let's go back and look at our data and see if that makes any sense. Does it? Well, what I see is, yeah, so the expected value is around 53. The minimum value is, yeah, if I subtract a half a psi from that, I don't quite get 52.6, but I'm in the ballpark. So yeah, this is actually a pretty accurate measurement, a pretty reasonable representation for the amount that things are changing in this measurement. Nice. All right. Now, I promised you there were two ways to calculate this, and that this is only one of them. So the other way to measure it is to go ahead and calculate x minus the expected value of x, that is to take what I think the error is. Keep in mind, this is what I think the error is. In reality, expected value of x is not actually xa. It's my best guess of xa, right? So this is what I think the error is for each measurement. And so to go back, right, what we're going to do is calculate the expected value of this mess here. All right, so we're going to do this in 2 steps. All right, so I'm going to do this 1 step at a time. All right, so so we've got an answer. Now, hopefully, if we use this other method, we should get the same answer, just using a different method. Okay, so 53.1, if I can type, minus 53.34. All right, so this one is negative 0.24. So I guess, is this the part where I can complain about Excel again? To be fair, it's not like the audience knowing it's an Excel plot is the end of the world. It's just, you know, it means you were, you know, basically using computing training wheels. Like, oh, okay, well, how good for you. 0.15, or 16, excuse me. 16. Whoops. All right, and 53.4 is our last one. This one should, should be very small. 53.4 should be 0.06, I think. Yeah. 0.06. There we go. All right, now we need to take the square of this. So, because that's what we're actually calculating the expected value of. So now we just need to square that. So 0.24 squared is 0.0576. 0.74 squared. So this is the part where we make them all positive, right? Remember, so yeah, remember all of these should sum to be 0. So we can't just take the expected value of this. That's going to be 0. So no, that was the whole reason for needing that square, was to make sure that doesn't happen. Okay, was 0.5476. So that one contributes a lot more variance. 0.76, it's going to be awfully similar. 0.5776. 0.16, 0.0256, and 0.06. Tiny. Basically nothing. All right, now the expected value of that is going to be useful to me. So let's start adding 0.0576 plus 0.5476. Plus 0.5776 plus 0.0256. Okay. So when I sum them all up, I get 1.212. Then I need to divide that by 5. Huh. Check it out. They are the same. So sure enough, I can calculate my standard deviation or my variance as a measure for the variability in a data set 2 different ways, and they always work out. Now, I want you to guess when I'm doing this in real life, when I actually need to analyze data, I want you to guess as to whether I do this by pen and paper and work it out excruciatingly like I'm showing you here, or do I just write 2 lines of Python and do it? Yeah, no. In reality, especially if you're working with big data sets, you're going to do this in a computer. The reason we work it out and actually suffer through doing this by hand is this notation gets super confusing if you can't picture in your head, or at least I find if I can't picture in my head, what's being subtracted by what when, and what is the procedure, and why is this all equivalent anyway. So this is useful to me. All right, so next time, thanks for paying attention. Next time we'll talk about what we do with this number and how it's useful and what we use it for. Thanks for watching.